Next, let's consider this n by n square matrix A. Assume that's the first row, second row, the ith row, the jth row, and the last row, the nth row. We know that if we take the entries in the ith row, multiply by the corresponding cofactors in the ith row, and then add them up, we get determinant of A. That's called a cofactor expansion along the ith row. So if we take the entries in the ith row, multiplied by the corresponding cofactors in the ith row, and then add them up. In the product, we get AI1 times CI1 plus AI2 times CI2. The last entry is AIN times CIN. This is the cofactor expansion along the ith row. They equal to determinant of A. Now think of this question. What if we take the entries in the ith row, multiply by the corresponding cofactors in the jth row, and then add them up? What do we get? What if we take the entries in the ith row, multiply by the corresponding cofactors, in the jth row, where I doesn't equal to j. That means we take entries in one row, multiply by the cofactors in a different row, and add the product. What do we get? What do we get? If I take an entry in the ith row, multiply by the corresponding cofactor in the jth row, we have AI1 times CJ1 plus AI2 times CJ2 plus AIN times CJN. What do we get? If I take the entries in one row, multiply by the corresponding cofactor in a different row, and then add them up, what do we get? So in order to find the answer, think of this. Let's consider another matrix B. Let B be the matrix obtained from matrix A by replacing the jth row with an ith row. Replace the jth row with an ith row. So let B be the matrix obtained from matrix A by replacing the jth row with an ith row. Consider matrix B obtained from matrix A by replacing the jth row with an ith row. So for matrix B, every row looks exactly the same as matrix A, except the jth row. We replace the jth row with an ith row. So from the jth row, the entries is AI1, AI2, AIN. Everything else stays exactly the same. So first row is A11, second row is A12, first row is A11, A12, A1N, second row is A21, A22, A2N. Ith row also stays the same. It's AI1, AI2, AIN. Continue, every row is exactly the same, except the jth row. I replace the jth row with an ith row. And also, last row stays the same. AN1, AN2, ANN. Think of this. In matrix B, if I take cofactor expansion along the jth row, what do I get? In matrix B, if I take the cofactor expansion along the jth row, what do I get? So think of this. Let B be the matrix obtained from matrix A. By replacing the jth row with an ith row. Assume I and j is not the same. Then in matrix B, take cofactor expansion along the jth row, what do we get? Next, in matrix B, take the cofactor expansion along the jth row. In matrix B, taking the cofactor expansion along the jth row, we get determinant of B. If we take cofactor expansion along the jth row, we get determinant of B. So determinant of B equal to the cofactor expansion along the jth row. That's the jth row here. Take the cofactor expansion along the jth row. I get AI1. Now here, for cofactor expansion, the sign is alternating. It's plus or minus j plus 1. That's the jth row. First column, -1 to the power of j plus 1 times the entry AI1 times the determinant of the submatrix times the determinant of the submatrix by removing the jth row in the first column. So matrix B, removing the jth row in the first column. Next entry is AI2. That's in the jth row, so the sign is -1 to the power of j plus 2. Since we don't know if j is even or odd, we can't tell if this is positive or negative. So write it as -1 to the power of j plus 2 times AI2 times determinant of the submatrix. That's in the jth row, second column. So times the determinant of the submatrix by crossing out the jth row in the second column. That's a submatrix of B obtained by removing the jth row in the second column. Continue, plus plus the last entry here. That's in the jth row, nth column. So the sign is -1 to the power of j plus n times the entries AIN times determinant of the submatrix by removing the jth row and the nth column, removing the jth row and the nth column. So that's the determinant of the submatrix of matrix B by removing the jth row and the nth column. Now, let's observe this submatrix. For matrix A and B, every entry is exactly the same, except the jth row. So, for this submatrix here, for each submatrix here, if I remove the jth row, in matrix B, if I remove the jth row, the submatrix is exactly the same as the submatrix in matrix A by removing the jth row, because the jth row is the only difference between these two matrices. So, this can be written as -1 to the power of j plus 1 AI1 times determinant of the submatrix AJ1. Since the only difference between matrix A and B is the jth row, if in both matrices I remove the jth row and the first column, they must be exactly the same. That's -1 to the power of j plus 2 times the entry AI2 times determinant of the submatrix matrix A, removing the jth row and the second column. Since between matrix A and B, the only difference is the jth row. If I remove the jth row in the second column, the submatrix in matrix A and B must be exactly the same. And continue, we get -1 to the power of j plus n times AIN times determinant of the submatrix. That's the submatrix obtained from matrix A by removing the jth row and the nth column. Because matrix A and B, they are exactly the same except the jth row. If I remove the jth row and the nth column, this submatrix, they are exactly the same. Now, what's this? If I take the sign, the positive negative sign, times the determinant, if I take the positive negative sign times the determinant, that's called the cofactor. That's called a cofactor in the jth row first column in matrix A. That's the cofactor in the jth row first column in matrix A. If I take the plus or minus sign times the determinant, that's the cofactor in the jth row first column. Same thing here. If I take the corresponding plus or minus sign times the determinant of the submatrix, that's the cofactor. That's a cofactor in the jth row second column. Plus here, if I take the corresponding positive negative sign times the determinant by removing the jth row nth column, that's the cofactor in the jth row nth column times the entries AIN. You can see that here. This expression is exactly the same as this expression here. AI1 CJ1 plus AI2 CJ2 plus AIN CJN. This expression is exactly the same as this expression here. And we know that in matrix B, there are two rows. There are two identical rows. These two rows are identical. So we know that determinant of B is 0. Since matrix B has two identical rows, we know that determinant of B is 0. So this expression must be 0. So this expression AI1 times CJ1 plus AI2 times CJ2 plus AIN times CJN must be 0, which means this expression is also 0. So in matrix A, if we take the entries in the ith row times the corresponding cofactor in a different row, and then add the product together, we must get 0. So therefore, keep it in mind. In a matrix, if we take entry in one row, multiplied by the corresponding cofactors, in a different row, then the sum of the products must be 0. The sum of their products is 0. So keep in mind that in any matrix, if I take the ith row times the corresponding cofactors in the ith row on the same row, and then adding up, we get determinant of the matrix. However, if I take the entries in one row times the corresponding cofactor in a different row, and then adding up, I get 0. I always get 0. And the same argument also works for columns, which means in a square matrix, if I take the entries of a column, multiply by the corresponding cofactors over the same column, and then adding up, add the product together, I get determinant of the matrix. That's called the cofactor expansion along the column. However, if I take the entries of a column times the corresponding cofactor along a different column, and then adding up, I always get 0. So keep in mind that the same argument also works for columns. For the same argument, if I change rows to columns, it's still true. Next, let's create an example. Let A be a 3 by 3 matrix. Compute A11 times C21 plus A12 times C22 plus A13 times C23, which means taking the entries in the first row times the corresponding cofactors in the second row, taking the entries in the first row times the corresponding cofactors along the second row, then adding up, and compute A12 times C13 plus A22 times C23 plus A32 times C33, which means take the entries in the second column times the corresponding entries times the corresponding cofactors along the third column, take the entries in the second column times the corresponding cofactors along the third column, and then adding up. So let's compute this. Let's first of all compute A11 times C21 plus A12 times C22 plus A13 times C23. Let's find the corresponding cofactors first. We know that the sign of the cofactors alternating is plus, minus, plus, minus, plus, minus, plus, minus, plus. For the cofactors along the second row, the sign is minus, plus, minus. So for C21, the sign is negative times the determinant of the submatrix. If I cross out second row, first column, I get submatrix 2, 4, 3, 2. That's negative 1 times 4 minus 12. That's negative 1 times negative A, which is positive A. Next, for C22, the sign is positive. Cross out second row, second column, what's left is these 4 corners. The sign is positive. What's left is these 4 corners. 1, 4, 5, 2. If I take determinant, I have 2 minus 20, which is negative 18. For C23, taking the cofactors on the third entry here. The sign is negative. Cross out second row, third column. What's left is 1, 2, 5, 3. Take determinant for the matrix 1, 2, 5, 3. 1 times 3 is 3. 5 times 2 is 10. I get negative 1 times 3 minus 10 is negative 7. Negative 1 times negative 7 is positive 7. Next, take an entry along the first row. So A11 times C21, A12 times C22, plus A13 times C23. Take the entries on the first row. I get 1, 2, and 4 times the corresponding cofactors around the second row. I get A, negative 18, and 7. Here, 1 times A is A. 2 times negative 18 is negative 36. 4 times 7 is 28. Altogether, we get 0. So, if we take the entries in one row, times the corresponding cofactor around a different row, and then add the product together, we always get 0. Same thing works for columns. Next, let's compute the corresponding cofactors around the third column. Let's compute the corresponding cofactor around the third column. For cofactors, the sign alternating. In the third column is plus, minus, plus. So, for C13, the sign is positive. Then times the determinant of the determinant of the submatrix by crossing out the first row, third column. What's left is a submatrix 2, 3, 5, 3. Two times 3 is 6. 4 times 3 is 15. So I get negative 9. For C23, we cross out the second row, third column. Here the sign is negative. For the submatrix, cross out second row, second column. We have a submatrix 1, 2, 5, 3. Then take determinant of the submatrix. 1 times 3 is 3. 5 times 2 is 10. 3 times 10 is negative 7. Negative 1 times negative 7 is positive 7. Next, compute C33. For C33, the sign is positive. Times the determinant of a submatrix by crossing out the third row, third column. If I cross out the third row, third column, I get this submatrix here. 1, 2, 2, 3. Then compute the determinant. 1 times 3 is 3. 2 times 2 is 4. 3 minus 4 is negative 1. So those are the corresponding cofactors around the third column. Next, take the entries around the second column. Take the entries around the second column times the corresponding cofactor around the third column, multiply and add them up. We have A12 A12 times C13 plus A22 times C23 plus A32 times C33. Take the entries in the second column. We have 2, 3, 3. Entries in the second column, we have 2, 3, 3. Times the cofactor around the third column. We have negative 9, 7, and negative 1. Negative 9, positive 7, and negative 1. Multiply, we get negative 18 plus 21 plus negative 3. Together we get 0. So if we take the entries in one column times the corresponding cofactor around a different column and then add them up, we always get 0. Next, let me introduce adjoint of a matrix. Let A be an n by n matrix with entries aij, where I and j is between 1 and n. So let A be an n by n matrix with entries aij. Let Cij be the corresponding cofactor of aij. Then the matrix formed by Cij in the ith row and the jth column is called matrix of cofactor from matrix A. So the matrix formed by C11, C12, C1n, C21, C22, C2n, and so on. This matrix is called matrix of cofactor of matrix A. We put the corresponding cofactors in exactly the same place. And its transpose, the transpose of this matrix is called adjoint of A, denoted by ADJ, adjoint of A. So if I find the transpose of this matrix, that means I put rows in columns. If I put rows in columns, I find the adjoint of matrix A. That's called adjoint of matrix A, denoted by adjoint of A. So if I put the cofactors in a matrix, this matrix is called matrix of cofactor of matrix A. If I find the transpose of this matrix, that means put rows in columns, this is called adjoint of matrix A. Next, let's create an example. Let A be a 3 by 3 matrix. Find the adjoint of A. In order to find the adjoint of A, let's first of all find the cofactors for each entry first. For the cofactors, the signs alternating. It's always plus, minus, plus, minus, plus, minus, plus, minus, plus. So for C11, the sign is positive. Then we take the determinant of the submatrix by crossing out the first row, first column. The submatrix here is 2, -4, 0, and 5. Then find determinant. 2 times 5 is 10. 0 times 4 is 0. We get 10. Next, for C12, the sign is negative. Then times the determinant of the submatrix by crossing out the second row, first row, second column. We get a submatrix 3, -4, -3, and 5. Then find determinant. 3 times 5 is 15. Minus -3 times -4 is positive 12. 15 minus 12 is 3, so you get -3. Next, for C13, the sign is positive. Times the determinant of the submatrix by crossing out the first row, third column. The submatrix is 3, 2, -3, 0. Then find determinant. 3 times 0 is 0. Minus -3 times 2 is -6. Double negative is positive. We get positive 6. Next, for C21, the sign is negative. Times determinant of the submatrix by crossing out the second row, first column. If I cross out second row, first column, I get the submatrix -1, -1, 0, and 5. Then find determinant. -1 times 5 is -5. Minus 0. Here, double negative is positive. We get positive 5. For C22, the sign is positive. Times determinant of the submatrix by crossing out the second row and second column. We get entries in the four corners, which is 1, -1, -3, and 5. Then find determinant. 1 times 5 is 5. -3 times -1 is positive 3. 5 minus 3 is 2. Next, find C32. Find C23. For C23, the sign is negative. And then times the determinant of the submatrix by crossing out the second row, third column. The submatrix is 1, -1, -3, 0. Then the determinant. 1 times 0 is 0. -3 times -1 is positive 3. 0 minus -3 is -3. And -3 is positive 3. Next, find C31. For C31, the sign is positive. And then times the determinant of the submatrix by crossing out the third row, first column. The submatrix here is 1, -1, -1, 2, -4. -1, -1, 2, -4. Then take determinant. -1 times -4 is +4. 2 times -1 is -2. Double negative is positive. 4 plus 2 is 6. Next, find C32. For C32, the sign is negative. Times determinant of a submatrix by crossing out the second row, third row, second column. The submatrix is 1, -1, 3, -4. Then take determinant. 1 times -4 is -4. 3 times -1 is -3. -3 is +3. -4 plus 3 is -1. And -1 is +1. Next, find C33. For C33, the sign is positive. Then times determinant of the submatrix by crossing out the third row, third column. The submatrix is 1, -1, 3, and 2. Then find the determinant. 1 times 2 is 2. Minus 3 times -1 is -3. 2 minus -3 is +5. So those are the cofactors for each entries. Next, let's find the matrix of the cofactors. The matrix of cofactors from A. Is in the form of C11, C12, C13, C21, C22, C23 in the second row, and C31, C32, C33 in the third row. So for the matrix of cofactor, the index looks exactly the same as matrix A. The index looks exactly the same as matrix A. A11, A12, A13, A21, A22, A23. The index looks exactly the same as matrix A. Next, let's plug in. So for the first row, we have 10, -3, and 6. In the first row, we have 10, -3, and 6. That's C11, C12, C13. In the second row, the entries is 5, 2, and 3. In the second row, the entries are 5, 2, and 3. 5, 2, and 3. In the third row, C31, C32, C33. The entries are 6, 1, and 5. That's the matrix of cofactor from matrix A. Next, for adjoint of matrix A, we take transpose for the matrix of cofactors. Take transpose for the matrix of cofactors, which means put rows in columns. For transpose, we put rows in columns. So put the first row in the first column, I get 10, -3, and 6. Put the second row in the second column, I get 5, 2, and 3. Put the third row in the third column, I get 6, 1, 5. This is the adjoint of matrix A. Next, let me show you a theorem. If A is an invertible matrix, then inverse of A is 1 over determinant of A times adjoint of A. That's another formula to find inverse of A. How can we prove this theorem? In order to prove inverse of A equal to this expression, we try to show that matrix A times this expression equal to an identity matrix. We try to show that matrix A times this expression matrix A times this expression equal to identity matrix. If I can prove that matrix A times this expression equal to an identity matrix, then this must be inverse of A. So first of all, we know that since A is invertible, then determinant of A is not 0. If determinant of A is not 0, then 1 over determinant of A is a scalar. That's a number, that's a constant. A is a matrix. Adjoint of A is that's another matrix. When we have a matrix times a scalar times a matrix, we can bring the scalar to the front. And equal to 1 over determinant of A times matrix A times adjoint of A. Assume matrix A. Assume A is a matrix. A11, A12, A1n in the first row. A21, A22, A2n in the second row. And AN1, AN2, ANn in the last row. Assume A is an n by n matrix. Then adjoint of A. For adjoint of A, we write the corresponding cofactors in columns. Write the corresponding cofactors in columns. Write C11, C12, C1n in the first column. Write the corresponding cofactor in columns. That's the transpose of the matrix of cofactors. So second column is C21, C22, C2n. And the last column is CN1, CN2, and CNN. That's the definition of adjoint. That's the definition of adjoint. We put a corresponding cofactor in columns. Then, when we multiply matrices, we take row times column. If I take row times column, what do I get? Here, for the first entry, take first row times first column, what do we get? If I take first row times first column, what do I get? If I take first row times first column, I get A11 times C11 plus A12 times C12 plus A1n times C1n. If I take first row times first column, that's what I get here. And according to earlier theorem, we know that if we multiply the entries in the ith row, multiplied by the corresponding cofactor in the ith row, and then add the product, we get determinant of A. Here, if I take the entries in the first row, times the corresponding cofactors in the first row, then together I get determinant of A. So if I take first row times first column, I get determinant of A. Next, row times second column. First row times second column, what do we get? First row times second column, what do we get? If I take first row times second column, I get A11 times A21 plus A12 times A11 times C21. A11 times C22 plus A2n, A1n times C2n. That's the entries in the first row of matrix A. And those are the cofactors. Those are the corresponding cofactors in the second row. Those are entries in the first row. And those are corresponding cofactors in the second row. And according to the earlier theorem, we know that if we take the entries in a row, multiplied by the corresponding cofactors in a different row, then the sum of their product must be 0. If we take the entries in a row, multiplied by the corresponding cofactor in a different row, then the sum of their products must be 0. Here we take the entries in the first row times the corresponding cofactor in the second row, then the sum of their product must be 0. And next entry, if I take entries in the first row times the corresponding cofactors in the third row, I must get 0. This is a transpose. This is a transpose of the cofactor matrix. So the third column represents cofactor in the third row. If I take the first row, entries in the first row, times the corresponding cofactor in the third row, I get 0. I get 0 everywhere. That's the first row. If I multiply, that's the first row. Now in the second row, I take second row times first column. That's the entries in the first row times the corresponding cofactor in the first row. That's the entries in the second row times the corresponding cofactor in the first row. According to the earlier theorem, their product must be 0. The sum of their product must be 0. Next, take second column, take second row times second column. That's the entries in the second row times the corresponding cofactor in the second row. Entries in the second row times the corresponding cofactor in the second row. I get determinant of A. And then the rest are zeros. If I take second row times corresponding entries in a different row. If I take an entry in the second row times the corresponding cofactor in a different row, I get zeros. And similarly, in the diagonal, I get determinant of A in the diagonal. And all other entries must be 0. I got the determinant of A in the main diagonal, and all other entries must be 0. Then, if I distribute determinant of A, if I distribute 1 over determinant of A to each of them, I get 1s in the main diagonal and 0s everywhere. If I distribute 1 over determinant of A to each entries, that's a scalar. If I distribute this scalar to each entries, I get 1 in the main diagonal and 0s everywhere. I get 1 in the main diagonal and 0s everywhere. This is identity matrix. This is identity matrix. Since A times this matrix equal to identity, that means this must be inverse of A. If A times this matrix equal to identity, that means this must be inverse of A. So let's complete the proof. So let's complete the proof. Right? Inverse of A equal to 1 over determinant of A times adjoint of A. That's another formula to find inverse of A. Next, let's create an example. In the previous example, find inverse of A using the new formula. Inverse of A equal to 1 over determinant of A times adjoint of A. In the previous example, that's matrix A. And that's adjoint of A. We try to find inverse of A using the new formula. 1 over determinant of A times adjoint of A. So let's find determinant of A first. For determinant of A, we can use cofactor expansion. Here in the third row, we have a 0 here. Let's find the cofactor expansion over the third row. On the third row, the first entry is -3 times determinant of a submatrix. -1, -1, 2, -4. That's 0 plus minus plus 5 times determinant of a submatrix. By crossing out the third row, third column, I get 1, -1, 3, 2. Next, find the determinant. I get 4 minus -2 plus 5 times 2 minus -3. That's -3 times 6 plus 5 times 5. -3 times 6 is -18. 5 times 5 is 25. Together is +7. So determinant of A is +7. And it's an adjoint. So for inverse of A, we do 1 over determinant of A times an adjoint, which is 1 over 7 times the adjoint 10, 5, 6, negative 3, 2, 1, 6, negative 6, 3, and 5. Then, when we multiply a matrix by a scalar, we distribute a scalar into the matrix to each entries. I get 10 over 7, 5 over 7, 6 over 7, negative 3 over 7, 2 over 7, 1 over 7, 6 over 7, 3 over 7, and 5 over 7. That's the inverse of A. How can we check the answer? If we want to check the answer, we take A times inverse of A. We must get an identity matrix. So let's check the answer. If I take matrix A, 1, negative 1, negative 1, 3, 2, negative 4, negative 3, 0, 5, times the inverse matrix, I must get an identity matrix. If that's correct, I must get an identity matrix. Here I get 10 over 7, 5 over 7, 6 over 7, negative 3 over 7, 2 over 7, 1 over 7, 6 over 7, 3 over 7, 5 over 7. Let's multiply. Take row times column. First row times first column, I get 10 over 7, 3 over 7, and negative 6 over 7. 10 plus 3 is 13. 13 minus 6 is 7. I get 7 over 7, which is positive 1. Next, row times column. 5 over 7 times 1 is 5 over 7, minus 2 over 7, minus 3 over 7. That's 0. Next, row times column. 6 over 7, minus 1 over 7, minus 5 over 7. That's also 0. Second row times column. 10 over 7 times 3 is 30 over 7. Negative 3 over 7 times 2 is negative 6 over 7. 6 over 7 times negative 4 is negative 24 over 7. 30 over 7 minus 4 minus 6 over 7 minus 24 over 7 is 0. Next, row times column. I get 15 over 7 plus 4 over 7 minus 12 over 7. 15 over 7 plus 4 over 7 is 19 over 7. 19 over 7 take away 12 over 7 is 7 over 7, which is 1. Next, row times column. I get 18 over 7 plus 2 over 7 minus 20 over 7. 18 over 7 plus 2 over 7 is 20 over 7. Minus 20 over 7 is 0. Next, row times column. I get negative 30 over 7 plus 0 plus 30 over 7. That's 0. Next, row times column. I get negative 15 over 7 plus 0 plus 15 over 7. That's 0. Next, row times column. I get negative 18 over 7 plus 0 plus 25 over 7. Negative 18 plus 25 is positive 7. 7 over 7 is 1. So here, A times this matrix equal to identity matrix. That means this is inverse of A. If A times this matrix equal to identity matrix, that means this is inverse of A. So the answer is correct. Next, let me introduce Kramer's rule. That's another way to solve system of equations. Let A be an n by n matrix with determinant of A not equal to 0. Then the system of linear equations AS equal to B has a unique solution. And the solution is S1 equal to determinant of A1 over determinant of A. S2 equal to determinant of A2 over determinant of A. Sn equal to determinant of An over determinant of A. Where A1, A2, An write as Aj. Aj is the matrix obtained from matrix A by replacing the jth column with the column vector B. So, assume A is the matrix A11, A12, A1n, A21, A22, A2n, AN1, AN2, and ANN. Assume that's matrix A. Assume B is a column vector. B1, B2, Bn. Then A1, it says, I replace the first column with the column vector B. So A1 is the matrix. A1, B2, Bn in the first column. The rest stays the same. A12, A22, AN2, A1n, A2n, ANn. That's A1. It's obtained from matrix A by replacing the first column with the column vector B. That's A1. And similarly, A2, in A2, I replace the second column with column vector B. The rest stays the same. It's like A11, A21, AN1. Second column become B1, B2, Bn, and the rest stays the same. The third column is A13, A23, AN3. That's the third column. And the last column is A1n, A2n, ANN. That's A2. In general, for AN, in matrix A, I replace the nth column with a column vector B. Replace the nth column with a column vector B. The rest stays the same. A11, A12, A21, A22, AN1, AN2. That's the first column, second column, third column, fourth column. All columns stays the same. And replace the last column with the column vector B. So the last column is B1, B2, Bn. That's A1, A2, An. So Kramer's rule says the solution to the system of linear equations is S1 equal to determinant of A1 over determinant of A, S2 equal to determinant of A2 over determinant of A, and Sn equal to determinant of An over determinant of A. So for S1, we take determinant for A1 over determinant of A, that's S1. Take determinant of A2 over determinant of A, that's x2. And for Sn, take determinant of An divided by determinant of A, that's Sn. So that's how we solve equations using Kramer's rule. That's another way to solve system of equations. Next, let's prove the theorem. Before we use it, let's prove it first. So first of all, we need to prove that the system has a unique solution. Then we need to show that that's the solution. So here, since determinant of A is not 0, then by equivalent statements, we know that the system AS equal to B has exactly one solution. Since determinant of A is not 0, by equivalent statements, we know that the system AS plus B, AS equal to B, has exactly one solution for every matrix B. Since determinant of A is not 0, then by the equivalent statements, we know that the system A is equal to B has a unique solution. And also we know that A is invertible. By equivalent statements, if determinant of A is not 0, A is invertible, which means inverse of A exists. Next, we try to show that this is a solution to the system. So here, from the equation, A is equal to B. Since inverse of A exists, if I multiply both sides by inverse of A, what do I get? If I multiply both sides by inverse of A, I get inverse of A times AX equal to inverse of A times B. And inverse of A times A is identity matrix. Identity matrix times X is X. So X equal to inverse of A times B. What's inverse of A? What's inverse of A? By the previous theorem, we know that inverse of A can be written as 1 over determinant of A times adjoint of A. Inverse of A can be written as 1 over determinant of A times adjoint of A. So S equal to 1 over determinant of A times adjoint of A times column vector B. That's a scalar. That's a matrix. That's a matrix. So we can multiply matrices first. That's a scalar. That's a matrix. That's a matrix. We can multiply matrices first. So leave the scalar by itself. That's a matrix. That's a matrix. Let's multiply the matrices first. Adjoint of A is the transpose of the cofactor matrix of A. Adjoint of A is the transpose of the cofactor matrix of A, which means I put the corresponding cofactor in columns. For each row, I put the corresponding cofactors in columns. So I get C11, C12, C1n in the first column, C21, C22, C2n in the second column, Cn1, Cn2, and Cn in the last column. Assume B is a matrix. Assume B is the matrix. It's a n by 1 matrix. B1, 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 B2, Bn. B is the n by 1 matrix. B has n row, 1 column. It's a column vector. Now, if we multiply, we take row times columns. If we multiply, take row times columns. If we multiply, take row times columns. So determinant of A stays the way it is. Multiply the matrices first. Take row times column. If I take first row times first column, I get B1 C11 plus B2 C21 plus Bn Cn1. That's the first row. Now take second row times first column here. There's only 1 column. Take second row times the column. I get B1 times C12 plus B2 times C22 plus plus Bn times Cn2. That's the second row. Continue. In the last row, we have take last row times the first column. Get B1 times C1n plus B2 times C2n plus Bn times Cnn. Then this is an n by 1 matrix. There's only 1 column. We have n rows. There's only 1 column. If I add this up, this is 1 number. So this is n by 1. This is an n by 1 matrix. This is a column vector. Next, I take the scalar, multiply to the matrix, which means I take scalar, multiply to every entries. If I multiply, the first entry here is B1 C11 plus B2 C21 plus Bn Cn1 over determinant of A. That's an entry in the first row. In the second row, take 1 over determinant of A times the entire row. I get B1 times C12 plus B2 times C22 plus Bn times Cn2 over determinant of A. Continue. In the last row, I get B1 times C1n plus B2 times C2n plus Bn times Cnn all over determinant of A. Here x is a column vector. That means that's x1, that's x2, that's xn. So x is a column vector. So we have x1 equal to the first row, b1 c11 plus b2 c21 plus bn cn1 over determinant of A. That's s1. s2. That's s2. s2 is b1 c12 plus b2 times c22 plus bn times cn2 over determinant of A. That's s2. Continue. Sn is the last row. b1 times c1n plus b2 times c2n plus plus bn times cnn over determinant of A. It's almost the same as an answer here. The denominator match is almost the same as an answer here. The denominator match, but the numerator doesn't match. We try to show that. Next, we try to show that this expression equal to determinant of A1, and this expression equal to determinant of A2. This expression equal to determinant of AN. Next, let's try to compute determinant of A1. What's determinant of A1? For determinant of A1, I can find the cofactor expansion around any row, any column. Here, since in matrix A1, I replace the first column with the column vector B. So here, let me take the cofactor expansion around the first column. So take cofactor expansion around the first column. Here, the sign for the first entry is -1 to the power of 1 plus 1 times the entry B1 times the determinant of the submatrix. Determinant of submatrix by removing the first row and first column. Plus -1 to the power of 1 plus 2 plus 1. That's the second row, first column. For B2, that's the second row, first column. Times the entries, B2, times determinant of the submatrix by removing the second row, first column. Continue until the last entry here. For the last entry, that's the nth row, first column. So the sign is -1 to the power of n plus 1, nth row, first column, times the entries Bn, times determinant of the submatrix by removing the nth row and the first column. Next, let's compare this submatrix with matrix A. In matrix A and matrix A1, the only difference is the first column. For every submatrix here, we remove the first column. For every submatrix here, we remove the first column. That means if I remove this column, if I remove the first row, first column in matrix A, I get exactly the same submatrix. If I remove the second row, first column, I get exactly the same submatrix. Since for matrix A and A1, the only difference is the first column. So, for the submatrix, if I get the submatrix from matrix A, I get exactly the same submatrix. In matrix A, if I remove the first row, first column, I get exactly the same submatrix. So if I obtain the submatrix from matrix A, I get exactly the same submatrix, since the only difference between matrix A and A1 is the first column. So if I obtain the submatrix from matrix A, I get exactly the same submatrix by removing the second row, first column. Continue. -1 to the power of n plus 1 times Bn times determinant of the submatrix obtained from matrix A by removing the nth row and the first column. And then we know that determinant of a submatrix times together with the sign, with the corresponding sign, that's the cofactor C11. Determinant of a submatrix removing the first row, first column, together with the sign, together with the plus minus sign, that's a cofactor C11 plus B2 times here the corresponding positive negative sign times determinant of the submatrix by removing the second row, first column, that's C21. Continue, we get Bn1 times the corresponding sign, the corresponding positive negative sign, times the determinant of matrix A, determinant of a submatrix, by removing the nth row, first column, that's the cofactor Cn1. Determinant of a submatrix by removing the nth row, first column, together with the plus minus sign, together with the corresponding plus minus sign, that's the cofactor Cn1. So this match the numerator here. B1 C11 plus B2 C21 plus Bn Cn1. This match the numerator. So numerator must be determinant of A1. So the numerator must be determinant of A1. Denominator is determinant of A. Similarly, for x2, we can do the same thing. We can show that determinant of A2 match the numerator here. Similarly, you can show that determinant of A2 match the numerator here. So that's determinant of A2 over determinant of A. And similarly, this numerator, in matrix AN, if I take cofactor expansion along the last column, the determinant must match the numerator here. In matrix AN, if I take determinant along the last column, the determinant must match this numerator here. So Sn is determinant of AN over determinant of A. That complete the proof. So that complete the proof of Kramer's rule. Next, let's create an example. Solve each of the following system of linear equations using Kramer's rule. If we try to use Kramer's rule, first step, write a system of linear equations in the form of Ax equal to B. So first step, write a system of equations in the form of Ax equal to B. Here A is the matrix, -2, 1, 3, -5. X is the unknown, X and Y. B is the constant on the right side, 4, 1. So that's A, that's X, that's B. In order to use Kramer's rule, check two things. Matrix A, first of all, matrix A must be a square matrix, and determinant of A cannot be 0. If matrix A is not square matrix, then Kramer's rule won't work. Or if determinant of A is 0, Kramer's rule won't work. So keep in mind that note. For any system of linear equations, in the form of Ax equal to B, if A is not a square matrix, or determinant of A is 0, Kramer's rule won't work. And we need to use Gauss-Jordan emulation. So we need to use Gauss-Jordan elimination. If A is not a square matrix, or determinant of A is 0, then Cramer's rule won't work. So in this case, we need to use Gauss-Jordan elimination. Now let's check. Here, A is a square matrix. How about determinant of A? Determinant of A is 10 minus 3, which is not 0. So since A is a square matrix, and determinant of A is not 0, we can use Cramer's rule. So here we can use Cramer's rule. So for Cramer's rule, first step, find A1, A2, A3, and AN. What's A1 here? For A1 for A1 in matrix A, replace first column with matrix B. In matrix A, replace the first column with matrix B. So I get 4, 1, 1, -5. In matrix A, replace the first column with matrix B. That's A1. For A2, replace the second column with matrix B. For A2 in matrix A, replace the second column with matrix B. We get -2, 3, 4, 1. And for A3, replace the third column with matrix B. Since there's no third column, we only have A1, A2. Next, find determinant of A1, A2. For determinant of A1, cross multiply. This is a 2 by 2 matrix. We can use a shortcut. Cross multiply and subtract. Again, -20 minus 1, which is -21. For determinant of A2, again, this is a 2 by 2 matrix. We can use a shortcut. Cross multiply and subtract. -2 times 1 is -2, minus 3 times 4 is 12. I get -14. Then, here, our S1 is X, S2 is Y. So X is determinant of A1 over determinant of A. Determinant of A1 is -21, determinant of A is 7. So we get X is -3. That's X1. X2, our X2 is Y. Our S2 is Y. So Y equal to determinant of A2 over determinant of A. Determinant of A2 is -14. Determinant of A is 7. -14 over 7 is -2. That's how we find X and Y. Next example, solve the system of equations using Kramer's rule. So in order to use Kramer's rule, first step, write the system of equation in the form of AX equal to B. So here, A is the matrix 2, -1, 3, 1, 3, -2, -3, -2, 1. That's A. X is the variables S, Y, Z. B is the constant on the right side. B is the constant on the right side. 3, -2, and 5. That's A, that's X, that's B. So first step, write the system of equation in the form of AX equal to B. Next, check two things. Matrix A must be a square matrix, and its determinant cannot be 0. If A is not a square matrix, or determinant of A is 0, then Kramer's rule won't work. We need to use Gauss-Jordan elimination to solve the system of equations. So first step, let's find determinant of A. Here A is a square matrix, that's fine. A is a square matrix, that's fine. Next, let's find determinant of A. For determinant of A, we can use cofactor expansion around any row, any column. Here, let me find a cofactor expansion around the first row. So for cofactor expansion, the sign of cofactor is plus, minus, plus. Minus, plus, minus is alternating. Plus, minus, plus. the sign of the cofactor is alternating. So let me take cofactor expansion around the first row. I get 2 times determinant of the submatrix 3, -2, -2, 1 minus -1 times determinant of the submatrix. By crossing out first row, second column, I get 1, -2, -3, 1 plus 3 times determinant of the submatrix. By crossing out first row, third column, I got a submatrix 1, 3, -3, -2. Then from determinant, we get 3 minus 4 plus 1 minus 6 plus 3 times -2 plus 9. 3 minus 4 is -1. 1 minus 6 is -5. -2 plus 9 is 7. 2 times -1 is -2 minus 5 plus 21. -2 minus 5 is -7. -7 plus 21 is positive 14, which is not 0. So since A is a square matrix and determinant of A is not 0, here Kramer's rule works. If Kramer's rule works, let's find A1, A2, A3 first. For A1, replace the first column in matrix A. Replace the first column with column vector B. I get 3, -2, 5. -1, 3, -2. 3, -2, 1. That's A1. For A2, replace the second column with column vector B. We get 2, -1, 3. Sorry, replace the second column with column vector B. First column stays the same. Second column is 3, -2, 5. Third column is 3, -2, 1. That's A2. For A3, replace the third column with column vector B. So first column stays the same. Second column stays the same. Replace the third column with the column vector 3, -2, 5. Next, find determinant for each of them. Find determinant for matrix A1, A2, A3. For determinant of A1, let's take cofactor expansion around the first row. I get 3 times determinant of the submatrix 3, -2, -2, 1 minus -1 times determinant of the submatrix -2, -2, 5, 1 plus 3 times determinant of the submatrix -2, 3, 5, -2. Then find determinant. 3 times 1 is 3. -2 times -2 is 4. Double negative is positive. -2 times 1 is -2. Minus 5 times -2 is -10. Plus 3 times -2 times -2 is 4. 5 times 3 is 15. Then simplify, we have 3 times -1 plus A plus 3 times -11. We get -3 plus A minus 33. Together we have -28. That's determinant of A1. Next, for determinant of A2. For determinant of A2, we can also take cofactor expansion around the first row. So take cofactor expansion around the first row. I have 2 times the submatrix 2, -2, -2, phi 1. Minus 3 times sum matrix 1, -2, -3, -1. Plus 3 times sum matrix, 3 times determinant of the sum matrix 1, -2, -3, -5, -3 positive 5. Then find determinant here. We get -2 minus -10 minus 3 times 1 minus 6 plus 3 times 5 minus 6. Simplify, we get 2 times a minus 3 times -5 plus 3 times -1. Together we get 16 plus 15 minus 3. That's 28. It's positive 28. Next, find determinant of A3. For determinant of A3, we can also use Cofactor expansion around the first row. So I get 2 times determinant of the sum matrix. By crossing out first row, first column, I get 3, -2, -2, 5. Minus -1 times determinant of the sum matrix 1, -2, -3, 5. Plus 3 times determinant of the sum matrix 1, 3, -3, -2. Then find determinants. 3 times 4 is 15. Minus 4. Double negative is positive. 1 times 4 is 5. Minus 6. Plus 3 times -2. Minus -9. Here, 15 minus 4 is 11. 5 minus 6 is -1. -2 plus 9 is 7. Then multiply. I get 22 minus 1 plus 21. 22 minus 1 is 21. 21 plus 21 is 42. So for the final answer, our S1 is X, S2 is Y, X3 is Z. So S1 is X. S1 is determinant of A1 over determinant of A. Determinant of A1 is -28. Determinant of A is 14. -28 divided by 14 is -2. Our S2 is Y. That's S1, S2, S3. Our S2 is Y. So S2 is determinant of A2 over determinant of A. Determinant of A2 is positive 28. Determinant of A is 14. 28 divided by 14 is 2. Next, X3. Our X3 is Z. X3 is determinant of A3 over determinant of A. Determinant of A3 is 42. Determinant of A is 14. 42 over 14 is 3. So that's the solution for X, Y, and Z. That's how we solve a system of linear equations using Kramer's rule. Next, we'll study section 3.1, Introduction to Vectors. First of all, let me show you geometric representation of vectors. Vectors, in general, can be represented by an arrow, which shows its direction and magnitude. So in general, vector can be represented by an arrow. The head of the arrow shows its direction, and the length of the arrow shows its magnitude. The head of the arrow shows its direction, and the length of the arrow shows its magnitude. Next, let me show you an example of vectors. That's vector u. That's vector v. That's vector w, for example. Those are examples of vectors. Now, for vectors, we have two operations called vector addition and scalar multiplication. For vectors, we have two operations called vector addition and scalar multiplication. How can we add two vectors? For example, for this vector u and v, how can we add two vectors? How can we perform u plus v? How can we add vectors u plus v? So, in order to add u plus v, we draw vector u first. Draw the first vector u first. Draw vector u first. Then, draw vector v. When we draw vector v, put the tail of vector v in the head of vector u. When we draw vector v, put the tail of vector v and the head of vector u. Draw vector v here. This vector and this vector are exactly the same vector. They point in the same direction, and their magnitude is exactly the same. This vector and this vector are exactly the same vector. Then, connect the initial tail and the final head. Connect the initial tail and the final head. This is the sum, u plus v. This is the sum of two vectors. That's u plus v. This vector represents u plus v. That's how we add vectors. Now, how about u plus v plus w? How can we add three vectors? So, when we try to add three vectors, draw vector u first. That's vector u. Add w, then draw vector w. Put the tail of vector v. Draw vector v. Put the tail of vector v and the head of vector u. Put the tail of vector v and the head of vector u. Shift this vector here. Shift this vector here. This is vector v. This vector and this vector are exactly the same vector because they point in the same direction and they have exactly the same magnitude. Next, add w. Put the tail of w and the head of vector v. Put the tail of w and the head of vector v. Shift vector w here. Shift vector w here. Then, connect the initial tail to the final head. Connect the initial tail to the final head. That's the sum of the vectors, u plus v plus w. That's the sum of the vectors, u plus v plus w. Next, How about scalar multiplication? For scalar multiplication, how can we multiply 2 times u? How can we multiply 2 times u? So for 2 times u, we draw vector u first. Draw vector u first. That's vector u. Then draw another vector pointing in the same direction, but the length is twice of vector u. 1u, 2u. Draw another vector pointing in the same direction, and the length is twice of u. This is a vector 2u. Draw a vector pointing in the same direction as vector u, and the length is twice of vector u. How about 3v? So for 3v, draw vector v first. Draw vector v first. Then draw another vector pointing in the same direction as vector v. The length is 3 times as vector v. That's vector 3v. It's the same vector pointing in the same direction as vector v, but the length is 3 times as vector v. Next, how about negative u? How can we draw the vector negative u? For negative u, we can consider this as negative 1 times u. So in order to draw negative u, let's draw vector u first. Draw vector u first. For negative u, draw a parallel line. Draw a parallel vector with exactly the same length, but pointing in the opposite direction. Draw a parallel vector with exactly the same length, but pointing in the opposite direction. This is a vector negative u. How about negative 2v? For negative 2v, let's draw vector v first. Then draw parallel vector. Draw parallel vector whose length is twice as vector v and point in the opposite direction. The length is twice as vector v and point in the opposite direction. That's the vector negative 2v. So that's all about vector addition and scalar multiplication. But how about vector subtraction and scalar division? Vector subtraction or scalar division can be done using vector addition and scalar multiplication. Vector subtraction, for subtraction of vectors, it can be done by using vector addition and scalar multiplication. For example, if we try to subtract 2 vectors, u minus v. If we try to subtract 2 vectors, u minus v, we consider this as u plus negative v. When we have u minus v, we consider this as u plus negative v. So for u plus negative v, draw vector u first. Draw vector u first. That's vector u. Next, draw vector v. Draw vector v. Put it here. Then, based on vector v, draw negative v. Based on vector v, draw negative v. So draw a parallel vector as vector v with exactly the same length, but pointing in the opposite direction. That's the vector negative v. Next, any 2 vectors, u plus negative v. So draw vector u first. Then shift vector v, shift vector negative v, point the tail of vector v to the head of vector u. That's the vector negative v. Together, connect the initial head, initial tail, and the final head. That's the vector u plus negative v, which is the sense u minus v. That's the vector u plus negative v, which is the sense u minus v. That's how we subtract vectors. How about division? How can we draw vector u divided by 2? For vector u divided by 2, consider this as half of u. Consider this as half of u, half times u. So for half of u, draw vector u first. That's vector u. Next, draw a parallel vector to vector u. The length is half of vector u. This is u over 2. This is half of u. Draw a parallel vector to vector u, but the length of the vector is half of vector u. That's u over 2. Next, let me introduce vectors in coordinate system. All elements in R, R2, R3, Rn are called vectors. For example, u equal to -1, 3. That's an element in R2, which is a vector. V equal to 2, 3, 4. That's an element in R3, which is also vector. They are vectors. U equal to -1, 3, that belongs to R2, that's a vector. V equal to 2, 3, 4, that's a vector, that's an element in R3, that's also a vector. Now, for vector in R2 and R3, we can draw the picture. For vectors in R2 and R3, for vectors in R, R2 or R3, we can draw the picture. How do we draw the vector U here? For R2, we can consider this vector is in SY plane. Consider this vector in the SY plane. Since U belongs to R2, consider this vector in the SY plane. In order to draw this vector, find a point -1, 3 first. In order to draw this vector, find a point -1, 3 first. Say -1, 3 is here. That's a point -1, 3. Now for the vector, we set the terminal point and the point -1, 3, and set the initial point and the origin. That's the vector -1, 3. That's the vector -1, 3. We set the terminal point and the point -1, 3, and set the initial point and the origin. That's the vector -1, 3. Now, how do we draw this vector in R3? For R3, let's consider the coordinate system with x, y, z axis. For R3, let's consider the coordinate system with s, y, z axis. Consider that's the x-axis, that's the y-axis, that's the z-axis. Let's plot a point 2, 3, 4 first. So the s coordinate is 2, y coordinate is 3, z coordinate is 4, s coordinate is 2. Y coordinate is 3. Let's plot a point 2, 3 on SY plane first. That's a point 2, 3 on the SY plane. on the xy plane, z coordinate is 0. Now when the z coordinate becomes 4, we raise this point, we can raise this parallelogram by 4 units. Raise this parallelogram by 4 units. We can raise this parallelogram by 4 units. When I raise the parallelogram, this point is also raised by 4 units. So that's the point 2, 3, 4. When I raise the parallelogram, I raise this point by 4 units. Then for vector v, set this point as the terminal point of the vector. Set the origin as the initial point. That's vector v. Set this point as the terminal point of the vector, and set the origin as the initial point of the vector. This is vector v. And for vectors in higher dimensional space, we are not able to draw a vector in a 2D paper, but we can describe the vector in exactly the same way. For example, if I let w equal to 1, 2, 3, 4, that's an element in R4. So w is also a vector. Here we can say that w is a vector in R4. Whose initial point is in the origin. And the terminal point is at the point 1, 2, 3, 4. So w is a vector in R4 whose initial point is an origin, and the terminal point is at the point 1, 2, 3, 4. We can draw w. We are not able to draw this w in a 2D paper, but we can describe w in the same way, in exactly the same way. Next, let me show you how to find vectors between 2 points. Let A equal to A1, A2, An, and B equal to B1, B2, Bn be points in Rn. The vector from A to B, denoted by vector AB, is defined as vector AB equal to B1 minus A1, B2 minus A2, Bm minus An. Consider this as head minus tail. Consider B is the head, A is the tail, for a vector from point A to B. Consider that's the head, B is the head, A is the tail. We use head minus tail. Take B minus A, head minus tail. So, for example, let A, B, be points in R2. Let C, D be points in R3. Find vectors AB, BA, CD, DC. For vector AB, B is the head, A is the tail, so use B minus A. Use B minus A. We take -3 minus 1, comma 1 minus 2. Together we get -4, comma -1. That's the vector AB. Now, how about vector BA? For vector BA, point A is the head, point B is the tail. we use head minus tail, A minus B. I get 1 minus -3, comma 2 minus 1. I get 4, comma 1. That's vector BA. Then for vector CD, we treat D as the head, C as the tail. We use head minus tail, head minus tail, -3 minus 2, 0 minus -1, and then 4 minus 0. Simplify, we get -5, comma 1, comma 4. That's vector CD. For vector DC, do the same thing. Head minus tail. Here, C is the head, D is the tail. Head minus tail. We get 2 minus -3, comma -1 minus 0, comma 0 minus 4. Simplify, 2 minus -3 is 5. -1 minus 0 is -1. 0 minus 4 is -4. That's the vector DC. And in general, vector AB is always negative vector BA. In general, vector AB is always negative vector BA. They are parallel vectors with exactly the same length, but pointing in the opposite direction. So in general, vector AB equals negative BA. They are parallel vectors with exactly the same length, but pointing in the opposite direction. Next, let me introduce vector operations. The U be U1, U2, Un, and V be V1, V2, Vn, be vectors in Rn, and the K be a scalar. Then, for vector addition, U plus V, we add the corresponding components, U1 plus V1, U2 plus V2, and Un plus Vn. That's how we add two vectors. And for scalar multiplication, K times U, we take K, multiply to each component in vector U. So I get K times U1, K times U2, K times Un. That's how we multiply scalar to a vector. Note, based on this operation, we can define negative V, negative U. We can define negative U as -1 times vector U, which means I take -1, multiply to each component in vector U. I get negative U1, negative U2, negative Un. So negative U is negative U1, negative U2, and negative Un. For negative U, we consider this as -1 times U, and we distribute -1 to each component in vector U. That's how we define negative U. And similarly, if we have U minus V, we consider this as U plus negative V. And we know that U is the vector U1, U2, Un. For negative V, that's the same as -1 times vector V. So I get negative V1, negative V2, negative Vn. Then add the corresponding components. We get U1 plus negative V1, U2 plus negative V2, and Un plus negative Vn. If we simplify, we get U1 minus V1, U2 minus V2, and Un minus Vn. That's how we subtract two vectors. So keep it in mind that U minus V is U1 minus V1, U2 minus V2, Un minus Vn. We subtract the corresponding components. That's how we subtract two vectors. And if k is not 0, vector U divided by k can be written as 1 over k times vector U, which is the same as saying I take 1 over k, distribute to each component in vector U. So I get 1 over k times u1 1 over k times u2 and 1 over k times un. That can be written as u1 over k, comma, u2 over k, comma, un over k. So keep in mind that vector u over k, if k is not 0, that's u1 over k, u2 over k, and un over k. We take each component, divide by k, if k is not 0. So those are some basic operations for vectors. Next, let's create an example. Let u and v be vectors in R4. Evaluate each of the following expressions. First one, u plus v. So for vector additions, u plus v, we add the corresponding components. -1 plus 4, 2 plus -1, 0 plus -2, and 3 plus 1. We get the vectors 3, 1, -2, 4. That's the vector u plus v. Next, how about the vector 3u? Let's call scalar multiplication. We multiply 3 to each component in vector u. I guess 3 times -1, which is -3. 3 times 2, that's 6. 3 times 0, that's 0. 3 times 3, that's 9. That's how we multiply 3 to vector u. Next, how about vector v over 4? For vector v over 4, take each component in v, divide by 4. 4 divided by 4 is 1. -1 divided by 4 is -1 over 4. -2 divided by 4 is -1 over 2. 1 divided by 4 is 1 over 4. That's vector v divided by 4. Next, how about 2u minus 3v? So for 2u minus 3v, we take 2, multiply to vector u first. 2 times -1 is -2. 2 times 2 is 4. 2 times 0 is 0. 2 times 3 is 6. Minus 3 times v. 3 times 4 is 12. 3 times -1 is -3. 3 times -2 is -6. 3 times 1 is 3. Next, we subtract the corresponding components. -2 minus 12 is -14. 4 minus -3 is 7. 0 minus -6 is 6. 6 minus 3 is 3. That's the vector 2u minus 3v. Next, how about the vector 4 times u minus 2v? For 4 times u minus 2v, do the parentheses first. U is the vector -1, 2, 0, 3, minus 2 times v. 2 times v, you take 2, multiply to each component in vector v. I get a, -2, -4, and +2. Then do the parentheses first. Subtract the corresponding components. -1 minus a is -9. 2 minus -2 is 4. 0 minus -4 is 4. 3 minus 2 is 1. Then, when we take 4, multiply to the vector, we distribute 4 to each component. We get -36, 16, 16, 4. Next, let me introduce linear combination. Let V1, V2, Vr be vectors in Rn. and let k1, k2, kr be scalars. Then the expression k1 times v1 plus k2 times v2 plus kr times vr is called a linear combination of the vectors v1, v2, vr. And the scalars k1, k2, kr, they are called the coefficients of the linear combination. Next, let's look at an example. Let v1 be the vector 2, 1, and let v2 be the vector 3, 4. Let v1, v2 be vectors in R2. Determine whether the vector w equal to 1, 2 can be expressed as a linear combination of v1, v2. So we try to determine whether w can be written as k1 times v1 plus k2 times v2. If we can find scalars k1, k2, let's make this equation true. Then we say w can be expressed as a linear combination of v1, v2. If we cannot find such scalars k1, k2, then we say w cannot be expressed as a linear combination of v1, v2. So here w is a vector 1, 2. We don't know k1. We try to find k1. v1 is a vector 2, 1. k2 is a scalar. v2 is a vector 3, 4. If I add the vectors, I have 2k1, k1 plus 3k2, 4k2. If I add the vectors, I have 2k1 plus 3k2, k1 plus 4k2. If 1, 2 equal to this vector, that means first component equal to the first component, second component equal to the second component. That means we have 2k1 plus 3k2 equal to 1, and k1 plus 4k2 equal to 2. Then we can write this as a matrix. The augmented matrix is 2, 3, 1, 1, 4, 2. That's the augmented matrix of this equation. If we observe this matrix, we can see that the first column match vector v1, the second column match vector v2, and the third column match vector w. So that's a shortcut to set down the equation. We can put vector v1 in the first column, v2 in the second column, and vector w in the last column. That's an augmented matrix. Then we can solve the matrix using Gauss-Jordan elimination. If we solve it using Gauss-Jordan elimination, I can first of all interchange row 1 and row 2. I get 1, 4, 2, 2, 3, 1. Next, I can multiply first row by -2, add it to the second row. So I keep first row the same. 1, 4, 2. Multiply first row by -2, add it to the second row, I get 0 here. Multiply first row by -2, add it to the second row. -8 plus 3 is -5. Multiply first row by -2, add it to the second row. -2 times 2 is -4. -4 plus 1 is -3. Next, I can divide second row by 5. Divide second row by -5. -1/5 R2. Second row is 0, 1, 3/5. First row is 1, 4, 2. Next, I can multiply second row by -4. Add it to the first row. So I leave the second row the same. Get 0, 1, 3/5. Multiply second row by -4, add it to the first row. 1 stays the same. -4 times 1 plus 4 is 0. -4 times 3/5 is -12/5. Negative 12 over 5 plus 2 is negative 2 over 5. That means K1 equal to negative 2/5. K2 equal to 3/5. That means K1 equal to negative 2/5. K2 equal to 3/5. So W can be written as K1 times V1 plus K2 times V2. We can check the answer. If I take negative 2/5 times V1 plus 3/5 times V2, here V1 is a vector 2, 1. V2 is a vector 3, 4. If I distribute 2/5, I get negative 4 over 5, negative 2 over 5. If I distribute 3/5, I get 9 over 5, 12 over 5. Then add the corresponding components. Negative 4/5 plus 9 over 5, we get 5 over 5, which is 1. Negative 2/5 plus 12 over 5, I get 10 over 5. 10 over 5 is 2. They equal to W. So K1 times V1 plus K2 times V2 equal to W. That means W can be expressed as a linear combination of V1 and V2. That means W can be expressed as a linear combination of V1 and V2. Next example, let V1, V2, V3, V4 be vectors in R3. Determine whether vector W can be expressed as a linear combination of vectors V1, V2, V3, V4. So here we try to determine whether W can be expressed as K1 times V1 plus K2 times V2 plus K3 times V3 plus K4 times V4. If we can find scalars K1, K2, K3, K4, that means W can be expressed as a linear combination of V1, V2, V3, V4. If we cannot find such scalars K1, K2, K3, K4, then W cannot be expressed as a linear combination of V1, V2, V3, V4. So let's set down an equation. W is a vector 1, 2, and 5. We don't know K1. V1 is a vector 1, 2, 1. We don't know K2. V2 is a vector 0, 1, 1. We don't know K3. V3 is 2, negative 1, negative 3. We don't know K4, but V4 is negative 1, negative 2, 1. Next, distribute K1, K2, K3, K4. 1 to 5 equal to K1, 2K1, K1. Distribute K2, I get 0, K2, K2. Distribute K3, I get 2K3 minus K3 minus 3K3. Distribute K4, we get negative K4, negative 2K4, K4. Then add the vectors. When we add the vectors, we add the corresponding components. So in the first component, we have K1 plus 0 plus 3K3 plus negative K4. So I get K1 plus 2K3 plus minus K4. That's in the first component. For the second component, we get 2K1 plus K2 minus K3 minus 2K4. For the third component, we get K1 plus K2 minus 3K3 plus K4. That's the third component. if these two vectors equal to each other, that means first component equal to the first component, second component equal to the second component, and the third component equal to the third component. So we have k1 plus 2k3 minus k4 equal to 1. First component equal to the first component, and then 2k1 plus k2 minus k3 minus 2k4 equal to 2. The second component equal to the second component, and then we have k1 plus k2 minus 3k3 plus k4 equal to 5, which means the third component equal to the third component. Next, we can write this as augmented matrix. The matrix here is 2, 0, 2, -1 equal to 1. 2, 1, -1, -2 equal to 2. Last row 1, 1, -3, 1 equal to 5. If we observe the entries, we can see that this must be 1 here, 1k1. If we observe entries, we can see that the first column match the first vector v1, second column match the second vector v2, the third column match the third vector v3, the fourth column match the fourth vector v4, and the last column match the vector w. So the shortcut of setting up the system of equation is put vector v1, v2, v3, v4 in these 4 columns, and put w in the last column. That's the shortcut to set up the system of equations. Put v1, v2, v3, v4 in the first 4 columns, and put w in the last column. That's the shortcut to set up the system of equations. Next, we can solve the system of equation using Gauss-Jordan elimination. So in the first row, we have a leading one already. Next, try to make everything below leading one to be 0. So I can multiply first row by -2, add it to the second row. So here, leave the first row the same. I get 1, 0, 2, -1, 1. Multiply second row by first row by -2, add it to the second row. I get 0, 1. -2 times 2 is -4. -4 plus 1 is -5. -2 times -1 is +2. 2 plus -2 is 0. -2 times 1 is -2. -2 plus 2 is 0. Next, I can multiply first row by -1, add it to the third row. I get 0, 1. -2 plus -3 is -5. +1 plus 1 is 2. -1 plus 5 is 4. Now move to the second row. Try to make the first non-zero entry a leading one. It is a 1 already, so try to make everything below leading 1 to be 0. So I can multiply second row by -1, add it to the third row. Multiply second row by -1, add it to the third row. I leave the first row the same here. Okay, 1, 0, 2, -1, and 1. Leave the second row the same. 0, 1, -5, 0, 0. Multiply second row by -1, add it to the third row. I get 0, 0, 0, 2. And 4 stays the same. Next, move to the third row. In the third column, it's impossible to make a leading one here. Then move to the fourth column, make a leading one here. I can divide the third row by 2. If I divide the third row by 2, I can make 1 here. I get 0, 0, 0, 1, 2. The rest stays the same. 1, 0, 2, -1, 1. 0, 1, -5, 0, 0. that's the leading one. We try to make all entries above and below leading one to be 0. So we try to make 0 here. I can directly add the third row to the first row. If I add the third row to the first row, I get 1, 0, 2, 0. 2 plus 1 is 3. The rest stays the same. 0, 1, -5, 0, 0, 0, 0, 0, 1, 2. Next, in order to find solution for K1, K2, K3, K4, write it back as equations. Here, this system is consistent, so we have solutions for K1, K2, K3, K4. That means W can be written as a linear combination of K1, K2, K3, K4. However, if this system here is inconsistent, that means that if there's no solution, that means we cannot find K1, K2, K3, K4. That means W cannot be written as a linear combination of V1, V2, V3, V4. Now here, let's solve an equation. This is consistent. Let's solve an equation for K1, K2, K3, K4. Write each row back as equation. First row can be written as K1 plus 2K3 equal to 3. Second row can be written as K2 minus 5K3 equal to 0. Last row says K4 equal to 2. Here, in the first column, second column, and the fourth column, there's a leading one. And in the third column, there's no leading one. That means K3 is a free variable. In the third column, there's no leading one. That means K3 is a free variable. So try to get K3, write everything in terms of K3. K1 can be written as 3 minus 2K3. K2 can be written as 5K3. K4 is 0. Leave it the way it is. So here K3 is a free variable. We can pick K3 to be anything. So let K3 equal to, for example, let K3 equal to T. So the solution is K1 equal to 3 minus 2T. K2 equal to 5T. K3 equal to T. K4 equal to 0. Sorry, K4 equal to 2. That's the solution. T can be any real numbers. T can be any real numbers. That's the solution for K1, K2, K3, K4. So let's pick solution. Let's pick one solution. There are infinitely many solutions here. Let's pick one solution. So if I let T equal to 1, then K1 equal to 3 minus 2, that's 1. K2 equal to 5 times 1 equal to 5. K3 equal to 1. K4 equal to 2. So we can write W equal to 1 times V1 plus 5 times V2 plus 1 times V3 plus 2 times V4. We can write W as a linear combination of V1, V2, V3, V4. If the system here is inconsistent, if we cannot solve for K1, K2, K3, K4, that means W cannot be expressed as a linear combination of V1, V2, V3, V4. So here we can check the answer. If we check the answer, 1 times V1, V1 is 1, 2, 1. 5 times V2, V2 is 0, 1, 1. Plus 1 times V3, V3 is 2, -1, -3. Plus 2 times V4, V4 is -1, -2, 1. If I distribute 1, I get 1, 2, 1. If I distribute 5, I get 0, 5, 5. If I distribute 1, I get 2, -1, -3. If I distribute 2, I get -2, -4, and 2. Then, when we add vectors, add the corresponding components. For the first component, 1 plus 0 plus 2 plus -2, that's 1. In the second component, 2 plus 4 is 7, 7 plus -4 is 6, 6 plus -4 is 2. In the third component, 1 plus 4 is 6, 6 plus -3 is 3, 3 plus 2 is 5. They equal to W. That means W equal to 1v1, 5v2, 1v3 plus 2v4. That means W can be expressed as a linear combination of v1, v2, v3, v4.